In this video, we're going to discuss empirical formulas and the calculations associated with combustion analysis. Combustion analysis is typically performed when an organic compound or some unknown compound is combusted. It's injected along with oxygen into a furnace where the sample is completely combusted. The products, if this is a hydrocarbon, for example, the products would be carbon dioxide and water. If there's excess oxygen, that's going to be still around as well. A water-absorbing substance will absorb the water molecules, and a carbon dioxide absorbing substance will absorb the carbon dioxide molecules. And then the increased mass of the water absorber and the increased mass of the CO2 absorber will allow us to figure out what mass of water was produced and what mass of carbon dioxide was produced. If there's only one other element in the compound that was combusted, the difference in masses will allow us to determine the mass of the leftover element as well. The empirical formula is the smallest whole number ratio of the elements in a compound, and it may not be the same as the molecular formula. For a molecule like water, H2O, the empirical formula and the molecular formula are the same. But for a molecule like hydrogen peroxide, H2O2, the empirical formula is HO, the simplest whole number ratio. We can determine empirical formulas from experiments like combustion analysis using the masses of the elements in a compound or the percent composition. If we don't have the masses of each element in a sample of a compound, we can assume that we have a 100-gram sample and easily convert those percentages into grams. From the mass, we'll need to convert into moles, and then from those moles, we can determine a mole ratio of the elements in the compound by dividing the number of moles of each element by the number of moles of the element with the fewest moles in the compound. The molecular formula cannot be determined without the molar mass, and there are other experimental methods like mass spectrometry to determine molar masses of compounds. But the molecular formula is going to be some multiple, maybe it's a 1 or 2, some whole number multiple of the empirical formula's subscripts. If you know the mass of the molecular formula, the molar mass, you can divide that by the mass of the empirical formula, the empirical formula's molar mass. That ratio will give you the integer n by which all the subscripts in the empirical formula would need to be multiplied to get the molecular formula. For example, if a compound has an empirical formula of CH5N, and we know that the molar mass is 62.12 grams per mole, we can determine the molecular formula for this compound by taking the 62.12 grams per mole and dividing by the empirical formula's mass, which was calculated by taking the molar mass of carbon plus the molar mass of hydrogen times 5 plus the molar mass of nitrogen, and that was 31.06 grams per mole. Anyway, the molecular formula's mass, 62.12 grams per mole, divided by 31.06 grams per mole, gives us approximately 2. And so that means the empirical formula is CH5N, but the molecular formula is twice that, C2H10N2. So here we have some mass percent data from a combustion analysis. A certain compound has 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen. Let's determine the empirical formula for this compound. Since percentages aren't masses, we're going to assume that we have a 100-gram sample of the compound. That means that our percentages will be their masses in grams. So we'll start with 71.65 grams of chlorine. To find a formula, we need moles. Formulas are mole ratios after all. So we're going to multiply by this conversion factor using the molar mass of chlorine, but upside down, in order to determine that we have 2.021 moles of chlorine in the 100 grams of this compound. We'll use our 24.27%, but write it as grams of carbon instead, and then use the molar mass of carbon to convert that into moles of carbon in 100 grams of the compound. Notice that we're going to have a 1-to-1 ratio, or a 2-to-2 ratio, or a 3-to-3 ratio of chlorine to carbon in this compound, because it's the same moles of each. All right, we'll do the same thing with hydrogen, 4.07 grams. Convert that into moles of hydrogen using the molar mass of hydrogen from the periodic table. And this time we get 4.038 moles of hydrogen. So now we have a mole ratio of the elements in this compound, but it's not the simplest whole number ratio. So we're going to take each number of moles and divide by the least number of moles. So we'll divide 2.021 by 2.021, and we'll do that twice. And we see that we get 1 to 1 being the ratio. And then 4.038 divided by 2.021 is going to give us, well, it's going to be about 2. So that means that these elements in the compound have a 1 to 2 mole ratio. So we know our empirical formula now. The simplest whole number ratio is Cl, C, H2. That's our empirical formula. Now that we know the empirical formula, let's assume we did some other analysis and we determined that the molar mass of the compound was 98.96 grams per mole. Can we determine the molecular formula? To determine the molecular formula, we're going to need to figure out what to multiply each of the subscripts by. To do that, we're going to need the empirical formula's molar mass. So we'll take the mass of chlorine, the mass of carbon, and the mass of 2 hydrogen atoms in order to determine the empirical formula's molar mass of 49.48 grams per mole. If this was equal to the molar mass of the compound, then we know that the empirical formula would be the molecular formula. It's not. So we're going to take the molecular formula's mass, the molar mass, and we're going to divide by the empirical formula's mass. So 98.96 grams per mole divided by 49.48 grams per mole is about 2. So 2 is going to be the integer that we're going to multiply each of the subscripts by to get the molecular formula. So for chlorine, 1 times 2 is 2. For carbon, 1 times 2 is 2. And for hydrogen, 2 times 2 is 4. Cl2, C2, H4 is the molecular formula for this substance. Well, now it's your turn to practice. Caffeine is a stimulant found in coffee, tea, and chocolate. It's 49.48% carbon, 5.15% hydrogen, 28.87% nitrogen, and 16.49% oxygen, and has a molar mass of 194.2 grams per mole. Can you use this information to determine both the empirical formula and the molecular formula for caffeine? Go ahead and pause the video now, solve this problem on your own, and then come back, unpause, and check your work with mine. All right, so how'd you do? See you next time.